Good morning, all of you. Now I am going to discuss about Unit 3, that is signal analyzers and digital meters. So, in this, the syllabus under the signal analyzers and digital meters are first one is wave analyzers. Under wave analyzers, we are having the frequency selective analyzers, heterodyne analyzers. And applications under applications of wave analyzers, we are having the harmonic distortion analyzers, and next spectrum analyzers, basic diagram of spectrum analyzers, spectral displays, vector impedance meter, Q meter. And under the digital meters, we are having peak reading and RMS voltmeters, digital voltmeters. Under digital voltmeters, which are using successive approximation, RAM and integrating type. These are the different digital voltmeters, and digital frequency meter is also there. Digital multimeter and digital tachometer are there. Coming to the first topic, wave analysis. So what is the meaning of this wave analyzer? We know that analyzing of a wave is nothing but called as a wave analyzer. So a wave analyzer is an instrument which is designed to measure relative amplitude of first single frequency components in a complex waveform. So any wave which is having different components like first order harmonic, second order harmonic, third order harmonic, like different harmonics will be there. You need to measure if you want to measure any one single particular frequency, so any particular amplitude at a single frequency, then this wave analyzer is used. This wave analyzer is having different components. Those are primary detector, a full wave rectifier, and indicating devices. Primary detector is consisting of LC circuit. So if L and C are connected in series or parallel, then it is used as a primary detector, and a full wave rectifier is used to convert the AC waveform into the DC waveform, and obtained DC voltage or current is measured by using the indicating devices. You can observe this is the block diagram of the wave analyzer. So the input of this wave analyzer, it is given to the primary detector. The output of primary detector is given to the full wave rectifier, so that you are obtaining the DC value, and this DC value is indicated by the PMMC galvanometer. And this is the you can read the output here. This is the block diagram. And coming to the circuit, here you can see this is the input given to the circuit, and in the primary detector you are using a L and C. This is the C capacitor, and this is instead of here inductor, you are using a coupled inductor here. This forms the primary detector circuit, and from the primary detector it is given to the full wave rectifier. So full wave rectifier, we all know that full wave rectifier is formed by four diodes, D1, D2, D3, D4, and a galvanometer is connected in the middle of this bridge circuit, PMMC galvanometer. So whenever a input signal is given here, the LC filter will filter the unwanted frequencies. It will filter the unwanted frequencies, and it will allow only one particular frequency. That means this LC circuit is tuned to a particular frequency, so that only one frequency is allowed, and the remaining frequency components are not allowed, they are stopped. That frequency which is allowed will enter into the full wave rectifier circuit. This full wave rectifier circuit will, what does it does is, it will rectify the AC voltage into DC voltage. That means the input current will enter here, and at this time D2 becomes forward bias, and it will be going through the PMC galvanometer, and this is coming again to the D1, so that this D3 will be forward bias, and like this. So during positive cycle, D2 and D3 are forward bias, while in negative cycle, D2, D3 are reverse bias and D1, D4 are forward bias, so that always you will be obtaining a DC voltage. That DC voltage is indicated by using the PMMC galvanometer. So this is the wave analyzers. And the different types of wave analyzers are frequency selective wave analyzer, heterodyne wave analyzer. Under the frequency selective wave analyzer means you will be selecting a particular frequency. A particular frequency is selected and that particular frequency is to be measured. Okay, now this is the input signal. This is given to the attenuator, input attenuator. So what is the meaning of attenuation? Attenuation means stopping. So this what does this input attenuator will does is it will stop only whatever the frequency it will we want that is allowed by the attenuator. The remaining frequencies are stopped here. Usually, this frequency selective wave analyzer is used for audio frequencies. That means having low frequency range low frequency range are using the frequency selective wave analyzer. So the low frequencies are allowed by the input attenuator and the high frequencies are stopped here. The input itself, this input attenuator will stop the high frequency and it will allow only the required low frequencies. So that low frequency waves are given to the driver amplifier. So this amplifier, what is the use of amplifier means this amplifier will amplify the signal. Suppose if you are having a weak signal obtained here, if you are getting a weak signal obtained here, if you want to strengthen that signal, then this driver amplifier will strengthen that signal. And this is given to the high Q filter. So here, see, a high Q filter, what does this does is what is the purpose is in this high Q filter, it will be having an RC circuit. So variable resistance and capacitances will be there. So if you vary the resistance and capacitance, this circuit will be tuned to a particular frequency. That means in the range which you are obtaining here, out of the range of frequencies, only a particular frequency is allowed at the output of the high Q filter. So that only particular frequency it is tuned at that particular filter at that frequency, so that frequency components are only allowed here. And at that particular frequency meter range attenuator, if that frequency is very much high, that means it is outer than our meter range, then it will stop that frequency signal. So meter range attenuator means the frequencies which are greater than the meter range, that frequencies are stopped by the meter range attenuator. And from this it is given to the output filter. This output filter will output amplifier, this amplifier will strengthen the signal or at the output side. It will strengthen the weak signal at the output side to the um, healthy signal. So that is given to the meter circuit, so that you can you see the output here in the meter circuit. And if you want to use this for other purposes, then it is connected to the output buffer, and from the output buffer it is given to the auxiliary output. So if you want to use this out for different purposes, this can be used here. So one circuit for the meter circuit if you want to measure, and if you want to use this for other auxiliary outputs also, you can use it. So that means here only particular selected frequencies are being analyzed here. So this is called a frequency selective wave analyzer, and this is the block diagram of the frequency selective wave analyzer. Next, coming to the heterodyne wave analyzer. So this heterodyne means mixing up. So mixing up of different signals is nothing but a heterodyne wave analyzer. So in this heterodyne wave analyzer, you will be having different frequencies. So that this is mainly used for frequencies of higher range. So that frequencies higher range, it is the input signal is given to the input attenuator, so that high frequencies are allowed here in terms of megahertz. So it will stop other frequencies, attenuate the other frequencies, and it will allow only the high frequency components. That high frequency components, if they are weak, then they can be amplified, they can be strengthened up by using the untuned amplifier here. Untuned amplifier. And this is given to the first mixer. So heterodyning itself means it is nothing but mixing up. So it is mixed up with some other signal. So that some other signal is coming from the local oscillator. So what does this oscillator does? Oscillator will provide any type of frequency what we want. Any type of frequency what we want. Suppose here we are fixing it to 30 to 48 megahertz range. We are getting the frequency, and the input is nothing but 0 to 18 hertz. So this first mixer, this mixer what does it does means it will take the difference of the two frequencies. That means the frequency which is coming from the input signal and the frequency which is set by the oscillator. So the difference of these two, here we are considering 18 megahertz is the input frequency and 48 megahertz is the oscillator frequency. So that if those two are mixed up, then you are getting a difference signal of 18 minus 48, that is 30 megahertz signal is obtained here. This 30 megahertz signal is given to the IF amplifier, that is intermediate frequency amplifier. So that means if that signal is weak, that can be amplified to the strengthened signal by using the IF amplifier. And the output from the IF amplifier is fed to the second mixer here. So second mixer here, at the second mixer, it is having inputs from the intermediate amplifier as well as the crystal oscillator. So crystal oscillator, and it will obtain the difference of these two signals. So the crystal oscillator frequency is automatically set to the frequency that is coming from the IF amplifier filter. So whatever the frequency it is there, that frequency is tuned for the crystal oscillator, so that it is the difference of these two signals you are obtaining as a zero signal, zero frequency signal. So that means as you obtain here 30 megahertz signal, so this crystal oscillator is also fixed to 30 megahertz signal. So the output is difference of these two is zero frequency, and the frequency 0 hertz is given to the active LPF, so that the that means low pass filter, so that that frequency only the fundamental components are being measured here, and that is shown on the meter circuit. Okay, this is about the heterodyne wave analyzer. So by mixing up of different frequencies you are able to you are able to measure the amplitude of a waveform. So that is about this is the block diagram of the heterodyne wave analyzer. And coming to the applications of wave analyzers. So these wave analyzers are used in the measurement of harmonic distortions. So whatever the harmonics present in the signal, that in that harmonics distortion, total harmonic distortion can be measured by the wave analyzer here. And also electrical measurements, and also sound measurements, vibration measurements. So in electrical machines, whenever you start an electrical machine, there is some amount of noise generated, and that noise and vibrations can be measured by using the wave analyzers. So these are the different applications of wave analyzers. In the next topic, we can know about the total harmonic distortion, how you are going to apply these wave analyzers in measuring the total harmonic distortion.